Okay, today's slide, we will be talking about a homework one, which will be summarizing the introduction to computer classifications and metrics, excuse me. I will share my screen right now to show what is happening over here. That is shown right over here. We have our introduction to computer classification metrics. We're just going to be going over the computer design and analysis. First key aspect that we'll be covering today will be the metric cost, which falls down to the design complexity, testing and packaging, yield impact, and to calculate using all of these factors, we can calculate our IC cost. Our IC cost can be determined using the design complexity, testing packaging, and yield impact. If once an equation is integrated, it will fall down to the wafer cost divided by the dies per wafer multiplied by the die yield. And from here over on, we can see an example for the Apple chips and their cost estimations. As seen, as the dice per wafer number increases, the cost for the IC is actually cheaper. So it also depends on the die, and as seen over here, the die increases, and once the die increases, the yield cost is still the IC cost is increases as well. Next will be the performance. The performance falls back to under the iron law, which is used to calculate the processor performance, which is a code size multiplied by CPI multiplied by the cycle time. Once that is all covered, we are then able to analyze and get architecture, and then from that we are able to implement the whatever the outcome is from the processor, and then do some realization and analysis. Next point will be the power point, which will cover pretty much like what is power for an example. Power is just the rate of the energy that a system is consumed by. In this computer architecture class, power is we can say the main aspect is just to identify the power consumption, the dynamic power consumption. In this case, we have dynamic power consumption is calculated using the capacitance of the system multiplied by the voltage multiplied by the areal frequency. And in this slide, we can see the excuse me, the equation over here on the side, and we can strategize the equation to either reduce power or increase power. For example, if we wanted to reduce power, we can decrease the voltage, and if we wanted to increase power, we can increase the voltage, and so as for the frequency and the capacitance in order to achieve a reduction in power or a gain in power. Next, we'll have the computer structure. A computer structure pretty much falls back to a CPU, memory, the input and output devices, and then a bus. The buses are what hold the input and output devices and the CPU as well, and they are like the core of a computer structure, as they hold the data transfer as well, and there can be summarized into being called a control unit pretty much in a computer structure. Moving on over here, we have a Flint's taxonomy. A Flint's taxonomy is just a way to identify like the best suitable data analyzation depending on a unit or its streams. For example, there's an SISD, an SIMD, an MISD, and an MIMD. An SISD is a single instruction, single data, which is direct point from one single to another. A single single instruction multiple data is the SIMD, which falls with the one control unit, and then it goes up to multiple streams. And then an MISD is multiple control units, and they all fall back to one data stream. And then last but not least is an MIMD with multiple streams and multiple control units, and they all fall back to one another. And that is mainly common in multiprocessor systems. Next, we have a RISC versus CISC, which is the reduced instruction set computer, and the difference between that and the complex instruction set computer. The comparison is that the RISC has simpler instructions, whereas the CISC has more and far complex instructions than an RISC. In terms of performance, an RISC aims for efficiency, whereas the CISC aims for powerful instructions. As for memory usage, an RISC uses more memory, although it is reduced, but it performs at a high level to achieve the best efficiency, which uses a lot of memory, whereas CISC uses less memory with complex instructions. Moving on over here, we have spec benchmarks. Spec benchmarks are an industry standard for evaluating CPU performance. So for example, over here in this slide, we can see that there are multiple spec benchmarks for a couple of different a couple of CPUs. So over here we have a graphics card in this example. Over here we have a Core i9 13th generation, 12th generation, 9th generation, and 11th generation. We can see that the most recent one, which is this 13th generation, has the best spec benchmark. The whole thing about it, a spec benchmark is pretty much like a how can I explain this? It's just like a metric, like a measurement for how good a processor is, or a CPU, or a RAM, or any software or hardware or devices that are in a computer. They go through a spec benchmark to evaluate which is the best. The geometric mean is used to calculate the overall spec rating. It provides a balanced performance measure across different programs. Moving on, over here we have parallelism. Underneath parallelism falls two laws: the Amdahl's law and the Gustafson's law. The Amdahl's law is the speed up of it is executed when problems, excuse me, the Amdahl's law happens when the problem size is fixed, whereas the Gustafson's law happens when the execution time is fixed. So in the Amdahl's law, to calculate the speed up of it, we would do 1 over 1 minus p plus pn. And as for the Gustafson, we would do n minus 1 minus n times s. Excuse me. The benefits of the Gustafson's law is pretty much it benefits the scaling with large problem sizes, and the Amdahl's law limits the parallelism due to serial portion. P in this case, P in this case is about the proportion of the program that can be parallelized, and the N is the number of processors. Overall, that was the lecture summary for lecture 2, which talked about key aspects of a computer structure. and in which we were talking about the computer classifications and metrics used. And that should do it for today's lecture summarization for homework one. My name is Mohammed El Shantaf. I hope this was helpful. Thank you.